Okay, so I'm going to talk to you tonight about dark matter. So you can see a nice picture of the stuff right there. Who has heard of dark matter before? Cool. Who knows what dark matter is? Okay, so that's kind of interesting. Like, a lot of people have heard about it, but not everyone knows what's going on. It's just a kind of catchphrase. So hopefully after this this talk, you'll have a little more understanding what it is, and you might be able to talk about it a bit more. See what physicists mean. For those people who were here last term, I apologize. It's like the exact same presentation I gave last time. Okay, so the outline, what I'm going to say today is basically I'll start with why would an astronaut care. So this stuff is very fundamental physics, so why might you be interested if you hope to be a future astronaut one day? Why would an astronaut want to learn? Why do they want to spend the next half an hour learning about dark matter? And then I'm going to talk about the premise for dark matter. So why do physicists think that there is dark matter? What lines of evidence do we have that suggest that dark matter is in the universe? Then I'll talk about dark matter candidates. So what are some of the explanations that physicists have come up with for this dark matter? Like what? It's obviously not regular matter that we know, so what is this stuff? And then I'll talk about the scope of dark matter. And I'll basically give you an idea. So like, is dark matter here in this room right now? Is it in our galaxy? Is it throughout the universe? Is it just in our one area, or is it somewhere else, or prevalent throughout the universe? So we'll talk a little bit about that. And then I'll just highlight some of the current experiments that are going through on detection of dark matter. So if there's interest in time, I can go into much more detail. Well, really into any of these points, but particularly into the direct detection. We'll see how time goes. So at this point, I should say that if you have any questions at any time, just ask, right? Don't hesitate to interrupt me. Okay, so why would an astronaut care? So this is a list from the CSA. I pulled it right off their website of the stuff that an astronaut would go through in their training in order to be prepared for their first launch. So I pulled it right off the website there, and you're not going to find physics up here. You're not going to find astrophysics, dark matter. It's that's not one thing that astronauts would focus on. But what you will find is space science. So there's one thing there. It's one item of like 20, so it's about 5%. So and obviously dark matter is one small component of that. So it's a very small bit in this CSA list here, but hopefully I can convince you with this next slide that it's a bit more important than that. So this is the NASA budget. I pulled this off the NASA website last term. So it has the budget over the 6-year period here. And you can notice that the total budget is somewhere between $18 and $21 billion of NASA, but the science component at the top ranges from $4.5 to almost $6 billion. So you're looking at 25%, say, of the budget goes directly to space science. And astrophysics specifically is $1 billion, so that's 5% just on astrophysics. So it's obviously, if the space agency does 25% of its funding to this stuff, then maybe it is worth an hour of your time to go over dark matter and try and understand it a little bit. Okay, so the premise for dark matter. So the story really starts in 1933 with Fritz Zwicky, who was a Caltech astrophysicist. He's a famous physicist. Some people say he's the greatest physicist never to win a Nobel Prize, actually. He was studying galaxy clusters, specifically the Coma cluster, in 1933. This is an image of the Coma cluster right here. So basically, so if you didn't know, the universe is, it's really big and it exhibits structure throughout the whole universe. So it's kind of like stars are correlated into galaxies, and then galaxies are often in clusters, and then these clusters form kind of like a web or filaments throughout the universe. So this is one example of a cluster, the Coma cluster. And it's basically all these little blue dots. So that cluster is blue shifted to us, and it's basically all these blue dots. These are all individual galaxies. So this is what Fritz Zwicky was looking at in 1933. And he used the Doppler shift, that blue shift in the light there, to determine the rotation velocity. So basically there's a direct relation between the wavelength that comes out of there, the wavelength change, and the rotation velocity of the galaxies through the center of mass of that cluster. So it's actually not a Doppler shift. It has to do with the expansion of the universe, but it's easiest to think of the Doppler shift. So if you didn't know what a Doppler shift was, it's like, so there's that fire truck moving, and if it's emitting a siren, a sound, then as the fire truck moves toward you, so it releases a crest, say, at this point here. at this point, and it releases, say the crest, the top of the wave, and then it moves slightly forward, and then it releases another crest. So the actual wavelength is compressed in the direction as it moves toward you. And then if you were behind the observer, then you would have the fire truck releasing a crest, and then it moves away and releases another crest. So that actually stretches the wavelength. So the next time, like you may have heard this before, when an ambulance goes by, you'll hear it go by, and you hear the pitch go up, 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 and then it'll go by you, and then you hear the pitch go down, down, down. And that's just the Doppler shift. That's exactly what's going on there. And this is the basic idea of what's happening with these galaxies. The speed of them relative to us is causing the light, the wavelength, to shift. So because it blue shifted, it would be corresponding to moving toward us for the coma cluster specifically. Okay, so that's how Fritz Zwicky took these Doppler shifts and measured this change in wavelength, and he got the rotation velocity. Then he took the virial theorem, which is basically it's just a theorem in physics that relates bound orbits. So it relates the energy of bound orbits, the kinetic and potential energies, and you can use that then. So he already has the kinetic energy because he has the speed because he has the rotation velocity from the Doppler shift, and then he can use the fact that it's a bound orbit to get the mass using the virial theorem. That's the basic idea. So he calculated this mass using the virial theorem and the Doppler shift, and then he compared this to mass estimates based on the brightness. So the brightness is basically, we know like our star emits a certain luminosity, a certain amount of light, and we know that it's because of the certain mass of our star. So you can look at how much light is coming from that galaxy, and then you can just directly correlate that to how much mass is in that galaxy. So obviously it's a little bit more complicated than that, but that's the basic idea. And then Fritz Zwicky, he took these two mass estimates and compared them, and he found that he had predicted about 400 times more mass for the gravitational effect through the Doppler shift and virial theorem. So this was called, he called this the missing mass problem, and later coined the term dark matter to explain this phenomenon. So that's where the term comes from, way back in 1933. So that's the galaxy cluster line of evidence. Is there any questions on that one? Okay, so there's three basic lines of evidence that have convinced astrophysicists of dark matter. This is one of them, galaxy clusters. So this is something that we see in many galaxy clusters throughout the universe.
But not all of them?
Not specifically 100%, but very nearly all of them. And there are explanations for the ones that aren't observed. So the next line of evidence is velocity rotation curves. So it's basically the velocity of, so that was on a galaxy cluster, on a galactic scale, the cluster scale. So you have all these galaxies in clusters, and you see dark matter in these clusters. And this is a line of evidence that dark matter is directly in our galaxy, or in spiral galaxies. So you take the velocity rotation curve. So here's a good example of a spiral galaxy. You can see the spirals very easily. This is the Pinwheel Galaxy, or M101. And what you can do is you can use the idea again of the Doppler shift to measure the rotation velocities of any of these stars way out here at a high radius from the center of the galaxy. And then you can measure that radius, so you can use the angular distance in the sky to get a length scale here. So if you just look at that theoretically, what you expect is, just like in our solar system, the further you go from the center of mass, the slower the rotation velocity. It's going to slow down. So you expect the exact same thing in a galaxy. You expect the velocity of those stars way out from the center of the galaxy to slow down, to go down.